Just like, oh, I need to return that, it didn't work out.
Thought you did. What'd you do this weekend? Oh.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, staying dry. It's really wet out there. I don't know why it was not okay to come to work yesterday, but it was okay to come to work today when today it's flooding even more, but you know, I don't make decisions right here, but okay. So today the plan is to continue where we left off last Thursday. And so last Thursday we kind of started our discussion about 2D direct stiffness problems. And so we're going to continue that today. We're going to take a look at what the element stiffness matrix looks like in 2D. And then we'll start using that for some problems. And so pretty straightforward today. We're just going to keep trudging along in our lecture notes, and then we'll go from there. Okay, so a couple announcements. I know I remember I literally just remembered right now that that I was going to push back the due date for homework set 1. So that's still going to happen, and so I'm going to push it back to next Wednesday. So the due date is going to be next Wednesday, whatever date that is, by 11:59 p.m. So the original due date is this Sunday, but because we're not going to finish up everything that you need for that homework assignment until probably this Thursday. And so I wanted to give you some extra time after we finish that to do the homework assignment. So the homework assignment will be due next Wednesday. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And so where we left off last time was truss problems and 2. Okay. So last Thursday, we were kind of working our way up to developing the element stiffness matrix in 2D. Okay. But we had kind of one main issue that that we were kind of working our way through last time. And that's mostly due to the fact that in 2 dimensions, you can have elements that are oriented in different ways. Okay. So very simply, right? So if we have a truss element that's oriented like this, okay? Okay. We have another truss element that's oriented like that. Okay. And so they can meet and they could be angled differently from each other. Okay. The reason this is an issue is that in 1 dimensions or in 1D, okay, which is just kind of generally implied because we only just have 1 dimension. But when we compute the deformation of one element, the direction anyway, it exactly lines up with the deformation directions in another element. Okay. So in 1D, and so one way that we can describe that is that the nodal degrees of freedom are all aligned in the same direction. Okay. So we kind of illustrate what that means. And so if we have an element that looks like this, okay, in 1 dimension, this will be connected to another element like that, okay? And so, normally we label this node 1, node 2, 3, okay? And so I'm just going to focus on the point where they touch, right? And so at node 2, right? If we're looking at the element on the left, right? We have D2 that's kind of being defined, that's going from left to right, right? Whereas if we draw the same thing for the second element, right? Second element is also connected to node 2. Okay. that D2 is going in the exact same direction. And so when we formed our global linear system, we didn't have to do anything extra, right? So the D2 direction of the first element and the D2 direction of the second element, they're perfectly aligned, right? And so when we form our, global stiffness system like this, right? And we input the entries for element A, okay, looks something like that usually. And we do the same thing for element B, okay, something like that, right? We could intersect these two without any issues because we know that at the point of intersection, right, both element A and element B have deformations that go in the same direction. Okay? So these overlap just fine because of that. Okay. All right, so we didn't have to worry about that. Now let's look at our 2D case. Okay, and I'll draw the same thing for you here. Okay. All right, so element A, I'm going to highlight in red, right? And so let me label the nodes here. So let me label this node 1, fixed to the ground. Node 2 is going to be where they meet. And node 3 is going to be fixed to the ground there. Okay. So if we look at the deformation for node 2 from element A's perspective, right? So we're given it in A. Okay. So what we're seeing here is that D2 is going parallel to that element. So it's going kind of up and to the right. Okay. Whereas for the other element, okay, element B is also going to be measuring D2, but it's going to be going up to the left. Okay. And so what we have here is a mismatch. Okay. The deformations from those two elements are not going in the same direction, right? And so when we combine these two elements together into one kind of global linear system, we have to be kind of really careful about it because the formulation for the element stiffness matrices are not going to match up. Okay. And so we have to come up with a better way or a more unified way to combine the element stiffness matrices of these 2D elements. Right? And so another way to kind of phrase that that statement there is that we need a standard coordinate system. We need a standard coordinate system to put all of our element stiffness matrices in relation to, so that we can adequately combine them together through the direct stiffness method. Okay. So that's kind of our goal. That's our goal for the next 30, 40 minutes, is to come up with the standard system and see what the element stiffness matrix looks like in this system. Okay. All right, so that's the motivation of kind of why we're going to be going through all these kind of change of coordinates and transformation matrices over the next 30, 40 minutes or so. Any questions on this? Okay. All right, so let's go and pick up where we left off last time. So last time, we were talking about this idea that if we have a vector, okay, so I'll call this U vector here, okay? We can describe the direction and magnitude of this vector relative to different coordinate systems. Okay. Description. So how we describe the vector depends on the coordinate system. Just like, how you describe an object depends on your perspective scene. Okay. And so on the one hand, one coordinate system that we talked about last time was kind of the standard coordinate system. Okay. So in 2D, our standard Cartesian coordinate system is we have the x direction going in the horizontal direction, the y direction going in the vertical direction. Okay. Right. But at the same time, we can have a rotated coordinate system. I think last time I went a little bit too extreme with the rotation, so I'm going to do a little bit of a nicer job this time. Okay. There we go. That was much better. Okay. So we'll call that x hat, y hat. And we're going to characterize this rotation by its rotation angle theta. Okay. So in order to get to x hat, y hat, we rotate our standard coordinate system counterclockwise by an amount of theta. Okay. So in purple right here, x, y, this is our standard coordinate system. And x hat, y hat, this is the rotated coordinate system. Okay. Okay. But it doesn't matter, if you're describing the vector in the standard coordinate system, or if you're doing it in the rotated coordinate system, the vector is exactly the same, right? So the vector is the same all throughout. It doesn't really matter what you call it or how you describe it, it's still going to be the same. Okay. And so last time we were working on this particular expression here, where if we have ux times I plus uy times j, okay? So this right here are the components of the u vector in the standard coordinate system. Okay. This must be equal to the coordinates of the vector in the rotated system. So this is going to be equal to u x hat times I hat plus uy hat j hat. Okay. So these are the components of the u vector in rotated coordinates, rotated system. So it doesn't matter how you describe the components, as long as everything kind of matches up and everything is consistent, then the left-hand side of this expression has to be equal to the right-hand side, okay? All right, so that makes intuitive sense, right? And so, the vector is not changing between the two, but right now this expression is not that useful because, we have one set of variables on the left and a completely set of different variables on the right, okay? Clearly, there's a relationship between them, but we need to be a little bit more explicit in how we do that. Okay. Okay. And so to kind of make this expression a little bit more useful, what we're going to do is we're going to substitute in for the unit vectors. Okay, so we're going to substitute in for these guys. Okay. It doesn't really matter which ones you substitute in for. You can substitute the ones on the left or the right. You just have to substitute for one of them. And what we're going to do is we're going to substitute expression in terms of I hat and j hat. Okay. So we're going to unify this a little bit. Okay, because what we can do is we can use geometry and trigonometry to come up with those expressions. All right. So let's go ahead and work on that. So let's work on I first. Okay, so let me go ahead and draw this triangle here. So the I vector we know is a unit vector in the standard x direction, right? So that means it's a horizontal vector and it has length 1. Okay. Let's draw a triangle. Okay. And in particular, I'm going to draw a triangle like this. Okay. Where I'm going to use the angle theta. That angle theta is the same angle theta that we're using in the rotation. Okay. Oh, that ended up perfectly. Perfect writing. Okay. All right. And so here I have A hat and B hat. Okay. So I drew these A hat and B hat vectors very intentionally, right? So the A hat vector is in the same direction as the rotated X hat. Okay. Okay. And this B hat here is in the Y hat direction. Okay. So let's come up with expressions for A hat and B hat relative to I. Okay. So based on trigonometry, okay, let's do A hat first. Okay. So the length of that A hat vector, if we use the hypotenuse of this triangle, so the hypotenuse of this triangle is the length of the vector I, okay? And then we're going to multiply that by cosine theta, okay? We know the length of the I vector is 1 because I vector is a unit vector, right? And so it has length 1 just by definition. We can do the same thing for B, okay? So the length of that side of the triangle B is going to be equal to the length of the hypotenuse, which is the magnitude of I, multiplied by sine theta. Okay. Where we know the length of the I vector is, again, 1. Okay. Right. So now that we know the lengths of the A hat and B hat vectors, we can use vector addition to substitute in for I. Okay. Oops. Okay. So by vector addition, we know I here is equal to A hat plus B hat. Okay. And so if you just follow the trails of the vectors, right? So if when you add vectors together, you go kind of head to tail, right? And so we follow the path, we go A hat, okay? Okay. And so if we go follow the path of A hat, we end up on this pink line here, okay? And if we add B hat to it, we're going to travel down this way, okay? And so we end up at this location here, okay? And so by vector addition, we have I is equal to A hat plus B hat, okay? Okay. We can substitute for A hat and B hat by multiplying its magnitude and its direction, okay? So the A hat vector is going to be equal to the magnitude of the A hat vector multiplied by I hat, okay? And the B hat vector is going to be magnitude of B hat times J hat, okay? Where I hat and J hat, remember, are unit vectors in the X hat and Y hat directions, okay? All right. So we've already solved for the magnitudes for the A hat and B hat vector, right? So they're cosine and sine theta. Oh, sorry. This one should be a minus sign here. Okay. Because the B hat vector, sorry, is in the minus Y hat direction. Okay. And so when we plug in for the magnitudes of A hat and B hat, we get I is equal to cosine theta I hat minus sine theta j hat. All right, so now we have an expression here for I, where we put it in terms of I hat and j hat. So what we can do now is we can take this expression, okay, and plug it in for I up here. Okay, so that's part one of our expression. Okay, we're going to do the same thing for j, where we're going to put j in terms of I hat and j hat. Okay, we're going to do the same thing. We're going to form a triangle. We're going to use trigonometry, sines and cosines in order to form that. Okay, and then we'll have everything we need from that expression to form our transformation matrix. Okay. Any questions on this so far? Just on kind of how we use that triangle there and kind of why all those expressions came to be? Okay. All right, so let's do the same thing for j. Okay, so j here is a vertical vector. Okay. So let me draw it. I'm just going to draw it slightly to the right, just to give myself a little more room. So this is the j vector, right? J vector is a unit vector in the standard y direction, so it just goes vertically up. Okay. If we once again break this down into components for the in the y hat and j hat directions, you get something that looks like this. Where this is the right angle. This is the angle theta. Once again, we have a b hat vector and an a hat vector. Okay. All right, so let's do this again. So we have a hat is equal to magnitude of j sine theta. Okay. Magnitude of j we know is 1. And we have b hat is equal to magnitude of j multiplied by cosine theta. Okay. Where again, this is equal to 1. All right, put these together. We know a hat is in the I hat direction. J hat here is in the j hat direction. Or b hat's in the j hat direction, sorry. Okay. What we get is j is equal to sine theta I hat plus cosine theta j hat. All right. So now that we have expressions for both I and j, we can plug this into our vector equivalency formula that we have above. Okay. All right. And so if we plug in for the formula above, we have ux multiplied by I. And so we plug in for I, we get ux times cosine theta I hat minus sine theta j hat plus uy. Uy is multiplied by j, so we have uy times sine theta I hat plus cosine theta j hat. Okay. This is all equal to ux hat I hat plus uy hat j hat. Okay. All right. So it seems like we're just making a mess. We're just throwing i's and j's and sines and cosines everywhere. But now what you'll see is that we have both I hats on the left-hand side of the equation and I hats on the right-hand side. And same thing with j hats. So what we can do now is we can group terms, group like terms, and form a system of equations. You want to group terms on left-hand side. Okay. Okay. So we're going to group terms on the left-hand side by I hat and j hat. Okay. And so if we do that, we get ux cosine theta plus uy sine theta I hat plus minus ux sine theta plus uy cosine theta j hat is equal to ux hat I hat plus uy hat j hat. Okay. All right. And so we can see from here is that, we can set the two I hat terms equal to each other. And so we can say that ux cosine theta plus uy sine theta is equal to ux hat. Okay. And we can set the j hat terms equal to each other. Okay. That means minus ux sine theta plus uy cosine theta is equal to uy hat. Okay. All right. So when you write the equations this way, it looks like a matrix set of equations. And so let's go ahead and extract the coefficients. And what we'll find is that we have something called our transformation matrix. Okay. All right. And so when we extract these coefficients, we have cosine theta, sine theta, minus sine theta, cosine theta, okay, multiplied by ux and uy is equal to ux hat, uy hat. All right. So let's debrief this for a second, because we threw a lot of, we've kind of come a long way here. So let's kind of debrief and kind of talk about exactly kind of what we're looking at here. Okay. Let's start with the vectors. Okay. And so we have ux and uy here. Okay. Let's remind ourselves what this is. Ux and uy, these are the components of our u vector in the original standard coordinates. Okay. So you have a standard vector. You want to describe it in terms of standard x and standard y. You use, ux and uy. Okay. On the right-hand side here, we have ux hat and uy hat. So these are the components of the same vector. Okay, but in terms of a different coordinate system, in terms of our rotated coordinate system. Right. And of course, that leaves our last thing here. Okay. So this last thing here is a matrix, right? You'll find that FEA, we love doing matrices here. So if everything we can transform into a matrix, we would. Okay. So this matrix here is called our transformation matrix. And the transformation matrix, that's the vessel that we can use to transform from one coordinate system to the next. Okay. Because ultimately, that's what this expression does. This expression lets us transform coordinate systems or coordinate descriptions from one system to the next one. Okay. And the way that we do that is we multiply it by this transformation matrix. Okay. All right. Any questions on this? All right. All right. So that's coordinate transformations in a nutshell. Okay. And so what we're going to do from here is that we're going to take this and we're going to apply it to our element stiffness matrix for our truss. All right, question. So does this matrix transform from standard to rotated or vice versa? This goes from standard to rotated. And so the inputs for this system are what's on the left-hand side. And so you basically feed it UX and UY in the standard components, and then you multiply by the matrix, and you end up in the rotated system after that. Yeah. So this right here is the result. And this one right here is the input. Yeah. So you're going from standard to rotated. Okay. So let's apply this to our truss element stiffness matrix. And so let me show it to you. Okay. And let's keep in mind that for our element stiffness matrix, we haven't been using this notation just because we've been in 1D. But technically, when we form our element stiffness matrix for a truss, it's in a rotated system. Okay. And so I'm going to use the hat notation for it. And so typically our element stiffness matrix looks like this. And so F1, F2, hat is equal to AE over L times 1 minus 1 minus 1, 1 times D1 hat, D2 hat. All right. So ultimately what we want is we want to transform those hat quantities into standard quantities. Okay. And so what you're going to see is that we need to do this twice, actually. So we need to do it for the forcing vector on the left and the displacement vector on the right. Okay. All right. All right, so let's go and get started. So the first thing we're going to do, okay. So this part's a little bit confusing here because everything we've been doing up to this point has X and Y components. Okay. If you look at this element stiffness matrix, there's no concept of X or Y because this is in 1D. Okay? Okay. Just because there didn't need to be. It was a 1D, it was a 1D element stiffness matrix for a 1D system. Okay. It may look that way because we have two nodes, but keep in mind that both node 1 and node 2 need to have X and Y components if we're going to move forward. Okay. So what I'm going to do is I'm going to do what I call augment this matrix. And so I'm going to add in some y components. For now, those y components are going to be 0. But we kind of need them to be there in order to move forward. Okay. All right. So our matrix is going to explode. And so instead of being a 2x2 matrix, it's going to be a 4x4 matrix. Okay? Because for each node, okay, so let's take node 1, for instance. Okay. Node 1 is going to have an x component. So we're going to have f1x and a y component, f1y. Okay. Same thing for node 2. So node 2 is going to have an f2x hat and an f2y hat. All right, so we're still going to have AE over L. So that's a constant that's just going to move through. Okay. That also means our element stiffness matrix is going to expand here. Okay. I'll explain the logic of kind of why I'm putting zeros and ones here in a second. Okay. And then we're going to do the same thing for the displacement. So we're going to have d1x hat, d1y hat, d2x hat, d2y hat. All right. So you may be wondering, why did I put all of those zeros into the matrix, right? We haven't done any transformation. We haven't applied our transformation matrix yet. And so this augmented system, this 4x4, is equivalent to the 2x2 system that I have up here, okay? And let me write something in here to make it a bit more clear, because in one dimension, we assume that we only had an x direction, right? And so this means that we have f1 x hat, or f1 x hat, f2x hat, d1x hat, and d2x hat. Okay. And so in one dimension, we only had deformation and forces in the local x direction, or the x direction that's local to that element. Okay. And so I preserved that here. And so if you looked at the locations for the ones and the minus ones, you see that they only correspond to the x direction, right? So d1x hat or d2y hat. Okay. Everywhere else is zeros because those are the y directions, which previously we didn't need. But now that we're going to be doing 2D problems, we need that y direction. For now, it's zeros, but it's not going to be zeros for long once we apply our transformation matrix. Okay. All right. Any questions on this so far? Okay. All right. So let's go ahead and let's start applying our transformations. Okay. So we need to transform two things. Okay. Or let's start with just one thing first, right? So let's start with just one side of the equal sign. But we need to apply the transformation to both nodes 1 and node 2. And so we're going to do it in this way. Okay? All right, because we know from our single node transformation, if we want to do f1x, f2, f1x and f1y hat. Okay. This is equal to cosine theta, sine theta, minus sine theta, cosine theta. Okay. Multiplied by f1x, f1y, right? That's just a straight up application of our transformation matrix. Okay. And same thing for node 2. And so for node 2, we have f2x hat F2y hat is equal to cosine theta sine theta minus sine theta cosine theta. Okay, and this is F2x, F2y. Okay. So both of these are just straight up applications of our transformation matrix, but individually for nodes 1 and node 2. Okay. So I'm going to make one substitution here just to save my hand because I save myself from carpal tunnel. So I'm going to use C. So C is going to be the same thing as cosine theta, and S is going to be the same thing as sine theta. Okay. So that's just from now on. Okay. So when you see C means cosine theta, S means sine theta. Okay. So this is fine, right? So these two matrices are fine. But the problem is that in our element stiffness matrix, we have both node 1 and node 2 as part of the same system. Okay. So we need to combine these two in the same way, right? And so we're gonna kind of do it in kind of an interesting way. Okay, because what we have in our element stiffness matrix is F1x hat, F1y hat, F2x hat, F2y hat. Okay. All right, so this is going to be equal to, so I'm just applying our transformations now. So it's going to be C S minus S C, okay? Because ultimately, we want to replace this with something with F1x, F1y, F2x, F2y, okay? Yeah.
Are you missing a negative on the sign?
It is right. This one right here, right?
Yeah.
Yeah, that's this one right here.
No, what about the other?
There's only one negative. The negative is only in the bottom left, and so the top right sign is positive.
Oh.
Yeah. Mhm. So continuing with this, we have 0, 0, 0, 0, and then we're gonna have the same kind of cosine sine pattern in the bottom right here. So cosine, sine, minus sine, and cosine. All right. So the reason I do this is because if you perform this multiplication, right? You have F1 x hat, F1 y hat is going to be multiplied by this, okay? The transformation matrices don't have any cross node interaction. So that's why we have all zeros in kind of these parts here. Okay. And then the same thing for F2. So F2 x hat, F2 y hat is equal to the transformation matrix only multiplied by the node 2 parts. Okay. All right. So we had to perform a little bit of kind of shadow linear algebra, I guess that's what I called it. So a little bit of finagling here just because we have a 2-node system. But we're now just about ready to kind of apply this. Okay. Because look at this expression here, right? Let's look at kind of this expression as a whole. Right? So on the left-hand side of this expression, we have things in the rotated coordinates. So everything with the hat. Okay. And what we have is we have an equal sign, and that's going to be equal to this gigantic matrix multiplied by things in the standard coordinates, which is what we want. Okay? All right. And so what if we take this? I'm just going to circle the right-hand side. Okay. So what if we take this and we plug in, you kind of come all the way up here. Okay. Why don't we just take that whole expression and plug in for that right there? Okay. And so that will accomplish what we need to do. Is we're going to get rid of the hat components and replace them with the standard ones. Okay. All right. So of course, this is going to be a lot of writing. And so, just kind of save myself again. Let's take this 4x4 matrix right here. And I'm going to call this the augmented transformation matrix. So I'm just going to call it R. Okay. And I'll put 2 underlines on it. Okay. So let's rewrite our element stiffness matrix with R. Okay. And so we're gonna perform 2 replacements here. So we're gonna replace the F hats with the with R and the F standard, and we're gonna replace the D hats as well. Okay. So we're gonna perform 2 substitutions here with R. Okay. All right. And so if we do that, on the left-hand side, we have R underline multiplied by F1x, F1y, F2x, F2y. Okay. This is equal to AE over L times 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. We're going to perform the same substitution for the displacement. So this is going to be an R matrix multiplied by D1x, D1y, D2x, D2y. Okay. All right, so this is looking really good because what you can see here from our 2 vectors, we don't have any hat components anymore. Everything is in terms of standard XY, right? We've taken the hats off everything. Okay. The only caveat, of course, is that we have these transformation matrices that are floating around. Okay. All right. So let's clean this up. We're in the home stretch right now. All right. So I want to get everything, all of the kind of sine and cosine terms on the right-hand side. So what we're going to do is we're going to pre-multiply by R inverse, okay? And so by pre-multiplying by R inverse, that's going to get rid of this R matrix on the right, okay? And it's going to move that R inverse to the, it's going to get rid of it on the left, move it to the right. Okay? We have F1x, F1y, F2x, F2y, okay, is equal to R inverse times AE over L times 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0, okay, multiplied by R times D1x, D1y, D2x, D2y. All right. And so I'm going to highlight kind of the middle portion of this. And so everything that involves our transformation matrix R, our original element stiffness matrix AE over L, and the second R transformation matrix, okay? Because we know everything here, right? Because remember, R is simply just this sine and cosine matrix up here, okay? So what we can do, okay, and I'll spare you the pain just because it's been a lot of linear algebra already. And so what we can do is we can perform, well, first of all, perform that inverse. Okay. And so after we perform that inverse, we can perform our matrix multiplication. Okay. And so what you're going to end up with is a lot of sines and cosines. Okay. But as a result of this, you know, this combination of terms right here, these three matrices multiplied together with the AE over L, that right there is our 2D element stiffness matrix. All right. So let's go ahead and do that. And so our 2D element stiffness matrix is given by the following. Okay. So we have AE over L. So the good thing is that that's just a constant. So that just kind of rides along through the entire process. And what you're going to have in here is a bunch of sine and cosine terms. Okay. All right. So then we have cosine squared, cosine times sine, minus cosine squared, minus cosine sine. Remember, this is a 4x4 matrix now because you know each of the nodes 1 and 2 have x and y components. Okay. And so this is going to be d1x, d1y, d2x, d2y. Okay. Next row in the matrix here is going to be cosine sine, sine squared, minus cosine sine, minus sine squared. Okay. Third row in the matrix is going to be minus cosine squared, minus cosine sine, cosine squared, cosine sine. Okay. Then the last row here is going to be a minus cosine sine. It's going to be a minus sine squared, cosine sine, and then positive sine squared. Okay. Remember, C here is cosine of theta, and S here is sine theta. Okay. Great. So you can see here that, you know, this matrix is much bigger. And so, you know, doing 2D problems is actually significantly more challenging than 1D problems, just because you have much bigger matrices to worry about. Okay. And by extension, you know, we're not going to go there in this class, but 3 dimensions, you can imagine, is even more difficult. As you can imagine, there's even more angles to kind of worry about in 3D, but we're not going to go there. We're gonna stick to 2D. Okay. All right. Any questions on kind of how we obtained this result here? Sure. Yeah. So you know, how we got here was kind of a desire, because, you know, we started out, you know, this is our 1D element stiffness matrix system here, right? And so we had F1, F2 is equal to AE over L times the 2x2 matrix multiplied by the vectors, okay, or the deformations. And so we wanted to kind of expand this to 2 dimensions. And so what we observed is that, you know, this system right here, both the forces and the deformations here are in the rotated coordinates, right? So they're in the coordinate system that's kind of parallel to whatever the element is. And so we're trying to accomplish kind of 2 things at the same time here. So on the one hand, you know, we want to take these local coordinates, which are the hat components, and transform them into the standard coordinates, right? Standard x and y. And so to do that, we need to make use of our transformation matrix that we have up here. So that's one goal that we had here. The other goal that we had here was to incorporate the second dimension here, which is the y. Okay. So that was kind of the first thing that we did. And so the first thing that we did was we kind of augmented this 1D system to include the y direction, right? And so that's kind of recognizing that node 1 has both x component and y components to do, right? And so let me kind of highlight this a bit better. Okay. Right, and so we kind of made this recognition that F1, okay, F1 that we started with in the 1D system had to be transformed into F1x and F1y, right? So we're basically adding a second y direction to that deformation, okay? Same thing with F2. And so F2 is being transformed to F2x and F2y, okay? Same thing with the D's. And so we have D1, that became D1x, D1y, and D2 became D2x and D2y, okay? So we were kind of preparing ourselves for the fact that there's going to be a y component to our deformations now, since we're going to be moving in 2D, okay? And for now, all of these components here have a hat because they're all in the local coordinate of the element, okay? All right, and then since we had to grow each node here by x and y, that means our matrix here would have to grow as well. And so we've taken this matrix and we've added zeros in kind of all the gaps in between. So the ones and the minus ones are still in the same location. They're all still relative to the x components here. It's just anything involving y, we added the zeros in between, okay? So that was step one. Step two was to take all of these hat components here, okay, and then apply our transformation matrix so that they would get back, so that they would be put in terms of the standard coordinates, okay? And so this is where the sines and cosines came into play. And so for the F1x, F1x hat, F1y hat, F2x hat, F2y hat, we had this kind of gigantic transformation matrix that we applied here. So we have cosine sine 0, 0, minus sine cosine 0, 0, and then kind of the same thing for node 2. Okay. Okay. And so we have the same thing for the deformations too. So D1, D2, X, Y, and so on. Right? And so the final step here was to kind of combine these two ideas. And so to take this this coordinate transformation, okay, so this essentially this relationship right here is a coordinate transformation. Okay. And we're going to take that coordinate transformation and plug it into our element stiffness matrix. Okay. Right. And we had to do that on two locations. So we had to do it for the forcing vector on the left, and then we had to plug it in for the displacements or the deformation vector on the right. And so what we have here is we have a transformation matrix multiplied by F is equal to the AE over L multiplied by R times the deformation vector on the right. Okay. And so we've kind of accomplished both goals at this point. We've added the y component and we've transformed back into the we transformed it back into the standard coordinates. And so the last thing that we have to do here is just kind of clean it up in terms of linear algebra to make it kind of a nice kind of clean package. And so we then move the transformation matrix over to the right-hand side of the equation by pre-multiplying, okay? And then on this last step right here, we did all the multiplications of the sines and cosines and stuff like that. So, in this step right here, there's a lot of kind of linear algebra, matrix multiplication that we're just kind of skipping just for the interest of time. And then we end up with this kind of monstrosity right here of a matrix. Okay. Any other questions on this, kind of how we got here? Okay. All right. So let's go ahead and do an example. So that's kind of enough derivation for one day. So let's kind of see how this is applied. I don't think we're going to finish the example today, but we'll start it, and then we'll kind of finish it up on Thursday. Okay. So in this example right here, we have a 2D structure, or 2D assembly of truss and spring elements. Okay. And so we have two truss elements and one spring element. Okay. All right, so this will be element A. Element A will be a truss element. Okay. This would be element B. Element B is a spring element. And element C will be a truss element. Okay, so we have three structural elements, and they're all kind of converging on the same point. Okay. All right. So we need to label the nodes. So we're going to call this node in the bottom left, we'll call that node 1. Okay. We're going to have node 2 that's attached to the first element. Node 3 that's attached to the spring. And we're going to have node 4 that's attached to the bottom element. Okay. All right. One thing that's going to be relevant for our problems is we're going to have angles here. Okay. And so we're going to say the angle between element C and element B is going to be 45 degrees. And then the angle between element B and element A is also going to be 45 degrees. Okay. All right. And so to form our element stiffness matrices, we need our structural and material properties. Okay. So elements A and C are both truss elements, and so these are going to have the same properties. And so they're going to have a Young's modulus, E, of 30 times 10 to the 6 psi. Okay. They're going to have a cross-sectional area of 2 inches square. Okay. And they're going to have a length of 10. All right. Element B is a spring, and so a spring only has one property, which is its spring constant. Okay. We'll say element B has a spring constant of 250,000 pound per inch. All right. And so based on the drawing that we have here, we can see that nodes 2, 3, and 4 are all fixed. And so those are all fixed to the walls. And so we need a force here. And so we're going to say that we have a force, a downward force of 10,000 pounds being applied on node 1. Okay. All right. And so in this problem, we want to compute. Okay. Well, we kind of know ahead of time that nodes 2, 3, and 4 are all fixed. And so the only node here that's free is node 1. Okay, so let's compute the deformation. And the X and Y directions. Of node 1. And of course, the way we're going to do this is we're going to use the direct stiffness. Okay. So we're going to use the same direct stiffness method that we used before. The biggest difference here is that since we're in 2D, our element stiffness matrices are going to be much larger than they were before. Okay. So it's going to be a lot more writing. We have a couple extra steps because we have to involve the angles. But you'll see it's the same process, just a little bit more annoying just because we have more writing to do. Okay. All right, any questions on this? Just the setup for the problem? Okay. All right, so let's go ahead and get to it. All right, so the first step in the direct stiffness method is to write out the element stiffness matrices. So we have 3 of these to write, so element A, B, and C. Okay. So let's start with element A. All right. So one thing that you're going to find that's useful for 2D problems is that your element stiffness matrix depends a lot on the angle. Okay. So before you start writing anything for the element stiffness matrix, I always find that it's useful to write out what the angle is. Okay. And then we're going to pre-compute sine of that angle and cosine of that angle, because we're going to be plugging that into our matrix. Okay. Okay, so let's look at element A. All right, so element A is that vertical element that kind of goes straight up like that. Okay. And so when I'm asking for this angle theta, okay, keep in mind that the angle theta that you plug in is the angle with respect to the positive x-axis, standard x-axis. Okay. And so you have to be a little bit careful here, because it's a little bit tempting looking at this figure here. If we look at element A, right, the angle that kind of jumps out to us from element A is 45 degrees. But that 45 degrees is with respect to element B, not the positive x-axis. Okay. And so if we look at the positive x-axis, right, the positive x-axis, if we started kind of right here, we kind of draw it that way. Okay. So relative to that positive x-axis, we have to rotate 45 degrees up to element B, and then another 45 degrees up to element A. So this angle here is actually going to be 90 degrees. All right, and so with theta is equal to 90 degrees, we can go ahead and compute cosine. Cosine of 90 degrees is 0, nice and easy. And then we have sine of 90 degrees, which is minus positive 1. Sorry. I get myself. All right. So this is really nice. And so when you have zeros here, basically any term that involves cosine is going to be 0. Okay. All right. So let me go ahead and write this down here. Okay. So you have Ka is going to be equal to A over L times we got cosine squared, cosine sine, minus cosine squared, minus cosine sine, cosine sine, minus cosine squared, minus cosine sine, sine squared. And if it seems like I'm kind of writing these in kind of a weird order, I'll go over that in a second. But let's do this first one kind of all from scratch, and then I'll show you kind of a more efficient way to do it. Okay. So d1x, d1y, 2x, d2y. Okay. I know we have to compute AE over L, but we'll do that in a second. Okay. The one I want to kind of focus on is just the U's here. Okay? All right, so let's go ahead and plug in for sine and cosine. We'll plug in for AE over L in a second. Okay. Okay. So we know that for element A, we know cosine of the angle is 0. Okay. And so we plug in for cosine squared, that's just going to be 0. Okay. Then we have cosine times sine, which is going to be 0 times 1. So that's also going to be 0. Okay. Then we have minus cosine squared, which is going to be a minus 0, which is just the 0. And then we have cosine sine, again, minus 0 times 1, which is just 0. Okay. All right, nice and easy. All right, next row. So next row, we have cosine times sine. Cosine times sine, again, is going to be 0. Okay. Next entry in the second row is going to be sine squared. And so sine is 1, so sine squared is also going to be 1. Okay. Then we have minus cosine sine. We know anything involving cosine is going to be 0 in this element. Okay. And then we have minus sine squared, which is going to be a minus 1. Okay. All right. So the next row in the matrix, you can see has everything in the next row involves cosine. So we know everything in this row is going to be 0. Okay. That's minus cosine squared, minus cosine sine, cosine squared, cosine sine, right? Everything involves cosine. And then we come to the last row in the matrix. And so with minus cosine sine, it's going to be 0. minus sine squared, which is going to be -1, cosine squared, which is 0, and then sine squared, which is 1. Okay. Okay. And then we have d1x, d1y, d2x, d2y. All right. And so when you have a 2D element, first thing is to establish what the angle is, compute what cosine of that angle is and sine of that angle, and then just start plugging and chugging, right? And so, it's kind of plug and chug on steroids here. It's a lot to do. All right, any questions on how we got this result here? Okay, so a couple things before we wrap it up for today. So first, I didn't forget. So let's compute AE over L. Okay, and so those, of course, depend on the material properties of the element. We have to be a little bit careful here because we have some mismatch of units. Okay, and so first thing we're going to do is our length here, which is in 10 feet. Let's convert that to inches. And so 10 feet is going to be equivalent to 120 inches. Okay. All right. And so when we compute AE over L, right, everything is in the right units then. So everything is in units. And so we plug it in, and what we get is 5 times 10 to the 5th pound per inch. Okay. So we can go ahead and put that factor out in front here. Okay. So those factors are just constant. So they're just kind of along for the ride. Okay. All right, and so the second thing that I want to show you before we end up today is to make your process a little bit more efficient, okay? And so let's look at the kind of the general form for the element stiffness matrix that we have here, okay? All right. One thing that you might have noticed about this matrix here is that it's a symmetric matrix. Okay? What that basically means is that if you draw a line down the main diagonal of the matrix, okay, you kind of split it like a ham sandwich, right? What you should see is that line there kind of acts like a mirror between the upper half and the lower half, right? And so if we look at this term, it has a mirror image right here, okay? If we look at this term, it has its mirror image right here, okay? And then this minus CS has a mirror image right here. And that's true for everything. So everything here has a mirror image. That's what it means to be a symmetric matrix, okay? And so you can use that information to kind of make your life a little bit easier. And so let me go ahead and rewrite this into kind of the form that I typically use for this matrix, okay? Because as it is right now, you have 16 terms here. And so 16 terms to compute, okay? Which is a lot. 16 terms is a lot. Okay? But if you know that this matrix is symmetric, you can kind of cut down on your work a little bit. So you compute something once, and you just kind of slide it into another part of the matrix. Okay? So let me go ahead and delete 6 terms from this system here. Okay. Okay. So I've gone ahead and deleted that lower half. Because what we know, based on what we've just seen, is that this part here is symmetric. And so when you're computing this element stiffness matrix, I would go row for row, but as you write in the rows, you can then reflect it down into their respective column, kind of reflecting across that, ham sandwich line, right? And so let's say that you start with this first row here, right? So the first row is always the first one you compute. And after you compute that first row, you can slide into their mirror image, locations right there, okay? So usually what I tell students is that you should write this row and then go into a column, right? So write the row and then reflect it into the column, row and then column, okay? So the first row kind of slides into the first column just like that. You can kind of imagine like a clock hand kind of moving down like that, okay? You can do the same thing for the second row, starting from the diagonal entry, okay? And so for the second row, you're gonna write in these three entries here and kind of slide those entries over, down, just like that, okay? And then same thing for the third row. You don't need to do it for the fourth row, because the fourth row, everything else is gonna be filled in at that point. And so for the fourth row, this CS kind of slides into its mirror image location there, okay? So you can use that trick to kind of save yourself a little bit of time in writing these matrices. So instead of writing and computing 16 different terms, you only have to do 10. I know it's not that big a reduction, but it's a reduction about 1/3. But it saves you a bit of time. And so we'll do a little bit more practice for this on Thursday as we finish up this example. And then, you know, hopefully you'll start to get a little bit of muscle memory for these things. Okay. All right. Any final questions on this before we wrap it up for today? All right, so thank you guys. Thank you guys for today. Hope you guys have a good rest of your day. Stay safe, stay dry. If you're driving home now, you know, definitely be safe, be careful on the roads. It's very slick out there. People also drive crazy in the rain right now, so definitely be careful of that. And I will see you all on Thursday. Thanks, guys. Have a good night. Good night. Good night, Nick. Yep.
Good night.
Have a good night. Hey. Hey, guys. You guys here for CFD?
Yeah.
How's that class going so far? I'm really excited.
So far, so good.
Nice.
Interesting to see the differences between your FAA class and 541 on this one.
Oh, yeah, because you guys are learning finite volumes, right?
Yeah. Right
Yeah.
now, we're on finite difference, but we're building up to finite volume.
Very nice, very nice.
There's a